Hello, gallery. I didn't look at you that much during the talk. Sorry about that. I know you're there. I appreciate you.
Thank you, Professor. Another amazing presentation, mind-blowing as always. I'm going to ask you something that's probably very naive, so I really do apologise being a layperson, but we can use general relativity, as you mentioned, to calculate the precession of Mercury. We can use it on our mobile phones so we can find each other on satellite tracking. We've now, of course, through LIGO, identified gravitational waves. Excuse me. So why is it still a theory of general relativity? Why isn't it a law, like we'll say, the first and second law of thermodynamics? Is it because we're just not quite 100% sure yet? That's always puzzled me, why it's not a law of general relativity. Thank you.
The answer is because the words law, theory, model, conjecture, hypothesis have almost no meaning whatsoever. There is the Newton's law of gravitation, the general theory of relativity, the standard model of particle physics, which sound weaker and weaker, but are stronger and stronger as we go in that. And that's just because scientists don't fret about these words and they don't update them. There's no threshold by which a plucky little hypothesis becomes a theory and then grows up to be a law or anything like that. You just have to ask for every single instance, how confident are we that we're on the right track? General relativity isn't right, by the way. It's not a quantum theory. It's a purely classical theory. So it's nothing that we currently know about the universe should be thought of as law-like in that sense.
Thank you very much over here. Hi.
Yep.
Thank you for your talk. So apparently the theory works really, really well, but you alluded to it already just now that it's not complete or it's not fully representing the universe. So what do you think is still missing to explain something like the Big Bangs at the very start, or singularities in black holes, or dark matter, dark energy? What's missing? What do we still need to know?
I mean, you think if I knew that, I'd just blurt it out here at the RI?
Fair enough.
I would write a paper. We don't know. I mean, you've done a very good job of listing some of the big questions to which we don't know the answer. The most fundamental one, perhaps, is that we don't know how to reconcile general relativity and quantum mechanics at any deep level. We can get them to play well in certain regimes, but not in the Big Bang or inside black holes, etc. There are features of cosmology and astrophysics like dark matter and dark energy. Also, the fact that there are more particles than antiparticles, things like that we can't yet explain. That's okay. That's what, gives us full employment. We're not done yet. We don't claim to be done yet. I once appeared on a radio show, Science Friday in the United States, and Ira Flato, the host, said, "You cosmologists, you only understand 5% of the universe. There's 25% dark matter and 70% dark energy. Aren't you embarrassed to only understand 5%? And I said, of the universe. It's 5% of the universe. I think that's very good. And if you think about what we understood a century ago, which is not crazy long ago, right? A century ago, we didn't know the universe was expanding. We didn't know about quantum field theory. We didn't even have quantum mechanics fully sussed yet. So yes, there are absolutely questions that we still have. I really do actually think that this question of reconciling general relativity with quantum mechanics will have unexpected implications for some of the other puzzles that you're asking about. I can't prove it yet, or I'd be writing the paper, not yammering here, but that's we all, as theorists, we sort of feel out our way forward, what we think is most promising.
What kind of things would you be looking for if someone could give you a LIGO that was really, really big, bigger than the planet, out in space?
What am I looking for?
What kind of features would you think might be interesting? If you can look really, really far back in time?
There's a longer thing to be said here, and I say that because I just put up a 4-hour solo podcast saying a bunch of things about how we're in a very strange situation in terms of the history of science right now, because we have theories, general relativity, but also the standard model of particle physics, which fit all of the data, but we know can't be right. That's an extraordinary frustrating situation to be in, because how do you move forward to make better theories? And I would even say that, to answer your question directly, we don't have a target for what to try to observe. The last time we had a target was when we turned on the Large Hadron Collider, and circa 2010, et cetera, we eventually found the Higgs boson in 2012, but many of us, including myself, were expecting and hoping to find much more than that. And we have not. And we might tomorrow, I don't know, but that was a very sensible place to look. The place where the Higgs boson is might very naturally have other particles there to be discovered, but they're not there. These days, we're peering very, very carefully at the cosmic microwave background, the leftover radiation from the Big Bang. My long shot thoughts about where to look are in violations of the fundamental symmetries of nature, like Lorentz invariance is the symmetry that goes back to special relativity. It says it doesn't matter how fast you're moving. What if there is actually a rest frame in the universe? Locality is a very important feature of physics as we know it, but there's hints from quantum gravity that it shouldn't be right at the exact level, so maybe could we observe one of those in the lab? We don't know how to do that. But these are all, cross your fingers and hope for progress. We know we're not right, so we have to do many things, not just one thing, and someone's going to get really, really lucky.
Thank you.
And when they do, they can present
We'll let
it
them
here.
know.
Exactly.
Yes.
Oh, yes, on the left.
Hi, thank you for the talk. This is probably a bit of a silly question. You mentioned that generally physicists assume that time is a quantity, has one dimension. But I was just wondering, why do we necessarily assume that if we think of space as having multiple dimensions and time and space are equivalent? Sorry, that's probably a stupid question.
Look, it seems very unfair that time only gets one dimension and space gets 3 dimensions, right? But so here's the problem if you imagine letting time have 2 dimensions. If you have 1 dimension, there's only one thing you can do, which is move forward in some sense. But as soon as you have 2 dimensions, like a plane, now you can go in circles. So all of those annoying time travel movies would suddenly be plausible. It'd be very easy to go backward in time if time had 2 dimensions. Now, that doesn't mean it couldn't or shouldn't be true, but maybe it hints at allowing time to have more than 1 dimension is incompatible with really respectable, well-formulated laws of physics. People have absolutely tried, by the way. It's not, I don't want to say anything, but most of the things you could have thought of, someone has tried. But trying doesn't mean you've tried in the right way. So people have tried, it hasn't worked out yet. Maybe tomorrow someone will try better.
I just want to say there's no such thing as a stupid question in this space. If you're thinking it, please ask it, because that's exactly what you're here for, so thank you.
I mean, that was a great question. There could be still stupid questions. I don't know.
I mean, yeah. I don't want to jinx it, but that could happen. Let's pop up to the gallery. The person with the microphone is going to have to choose some people because I cannot see.
Yeah, you're all silhouettes to us. Okay.
So Verity should be there. Yeah.
Hello. Can you just explain what the geometric interpretation of the left-hand side is? You said it's not curvature, right? So it's like a renormalized curvature, or?
No, it is. So it is. Sorry, I moved my microphone. It is part of curvature. So basically, what Einstein. So the Riemann tensor, R lambda rho mu nu, is all of the possible ways to answer that question: how do those initially parallel lines deviate from each other? What Einstein is telling us is that gravity doesn't immediately affect, or I shouldn't say gravity, what I should say is energy and momentum do not immediately affect every single possible answer to that question, every single possible manifestation of curvature. And in retrospect, that's true, because a gravitational wave can exist in what is otherwise empty space. So even without any energy momentum tensor, right? Even without any mass or energy or whatever, you could have completely flat space-time, or you could have a gravitational wave going through, etc. So this is a higher level mathematical discussion, but basically Einstein is saying that energy and momentum directly lead to some kinds of curvature. Other kinds are able to propagate out there even without energy momentum along.
Thank you. And we've got a question from the left-hand side of the gallery at the top there.
Just up here. Given you were saying there's nothing particularly special experientially, potentially, about going across the event horizon, it's just more like a mathematical solution, is there anything to preclude black holes within black holes? And if there's enough mass, effectively, could we all be in a black hole right now, which is sufficiently large enough, given the mass, the observable universe? And I think I've read at some places that the observable universe is effectively flat geometry. So if it was much larger, then it might be curved at the edges versus what we see. I don't know if I phrased that well. But.
No, I totally get it. So the rule of thumb, whenever you're talking to a physicist and you begin a question with, is it possible that? The answer is yes. It's possible that we are in a black hole. It doesn't seem to be right. It doesn't seem to be the kind of universe we live in. A black hole is a region of space-time with the property that once you enter that region, you can never leave, and in the future, you will hit a singularity. Our universe doesn't quite seem to have that property that you can never leave, and in fact, we have a singularity in the past called the Big Bang. So if anything, our universe is kind of like a white hole, a black hole backward in time. But it's absolutely possible, like you say, that conditions can be very different outside the observable universe, and maybe if we wait long enough, everything will collapse again into a singularity, and it'll be true that we are in a black hole. But more concretely, your other idea, could I take a small black hole and just throw it into a big black hole and have a black hole inside a black hole? Sure, feel free to do that. No one on the outside will be able to tell, but you'll have a feeling of accomplishment.
Thank you. Yep, we'll go just down here.
Do you envisage that there's going to be the possibility of some big leap forward with the advance of artificial intelligence? And if so, how would that be useful for understanding, for humans to understand it? Or are there ways that it can reach some answer and we can't really understand how it's got there?
Yeah, this is a very intriguing question for not just doing science, but for all sorts of fields. How will artificial intelligence help us leap forward? I mean, I have used ChatGPT, et cetera, in my work, but not to invent some clever new theory of the universe. It's like, what is the letter they use to represent this constant again? And ChatGPT is very good at getting that 90% right. But the current generation of large language model implementations of AI do not have, in any concrete, definable way, what we call a model of the world. You know, they do not have symbols in their memory representing gravity and space and things like that. They're language models. They are trained to string together sentences and paragraphs in ways that are trained on sentences and paragraphs that have been strung together by human beings in the past. The first thing I did when I got access to GPT-4 was to ask it some of my favorite difficult puzzles in physics and philosophy. And it was instantly like just giving me the usual answers to them because that's what it is trained to do. It is absolutely conceivable that as they get better, they will get better at going beyond what human beings have said. But right now, it's all about interpolation, not about extrapolation. And so I think that AI will be useful in the same way that pocket calculators are useful, but you're not going to give a pocket calculator tenure in a math department, right? It's doing a different kind of thing.
Thanks for an amazing talk. Everything that you've presented this evening kind of implies that time and space are absolute. But thinking back to quantum field theory and, for instance, the implications of last year's Nobel Prizes, could you comment on the potentially emergent properties of time and space? Thank you.
I mean, I could. What time is it now, and how long do you plan to be here are my next questions. What is the best thing to say here? I'll try to distill it down to 2 points. Last year's Nobel Prize went to people who tested what is called Bell's inequality. So in the quantum world, there was a feature of quantum mechanics that was first discovered by Albert Einstein in 1935. One of the reasons why I think he is underrated, if anything, which is that there is what we call entanglement between different quantum particles. So if you have two particles that are spinning, for example, and you know if you look at one of them, it'll either be spinning clockwise or counterclockwise. You have no way of predicting what you will see. And if you look at the other one, it'll be spinning clockwise or counterclockwise. You have no way of predicting what you will see. But you can predict that they will be spinning oppositely. That is something that quantum mechanics allows you to do. So Einstein and his friends Podolsky and Rosen said, what if I take these two particles, I don't observe them, I separate them by many light years, and then I observe my particle right here and my friend 4 light years away, I know what they're going to see. And it turns out that if you really look at this carefully, this seems to be violating the spirit of special relativity. How did the information about what the spin should be get from here to there instantaneously? But it doesn't violate the letter of the law because no physical thing moved, and the information that moved is useless because your friend doesn't know what answer you got. So you can't actually use this apparent faster-than-light communication to actually send information. So this fact remains a central feature of quantum mechanics, that it seems to involve what Einstein called spooky action at a distance without actually violating the letter of the law concerning special relativity. What are we to make of that? And I have a hot take on this, okay? Everyone in the field is trying to wrap their brains around how can you get this kind of locality, this kind of non-locality out of what we know about quantum mechanics and space-time in a way that is consistent, etc. I think, based on the last talk I gave at the RI on quantum mechanics and the many worlds interpretation, that the fundamental laws of physics have no locality built into them at all. That locality, by which we mean the fact that if I poke the universe at one place, nothing changes instantly far away. The changes ripple out at the speed of light or more slowly. That's the weird thing. That's what has to be explained through the emergence of space-time in a truly quantum theory of gravity. And the deep question is not how can you allow for this weird non-local correlation in quantum measurements, but rather why does the universe look local at all? And I think that that's actually a plausibly answerable question. And when I'm not giving talks, I'm doing research on answering that question. So hopefully we'll get an answer.
Thank you. We had one in the gallery up here.
Thank you for the talk. Could you explain how relativity relates to some of the other more recent theories like string theory or the concept of a wormhole? Is it by implication or are they brand new theories on their own?
Good. Wormholes and string theory are two very different things. Wormholes are straightforwardly similar, in fact, not even similar. They're hidden in this equation right here. This is the Schwarzschild metric for empty space in the presence of general relativity and spherical symmetry. So I just mentioned Einstein, Podolsky, and Rosen, the famous EPR paper about quantum entanglement. The same year, Einstein and Rosen, without Podolsky, wrote the first ever paper that examined wormholes. They looked at this equation and they realized if you extend it in certain ways, it actually implies the existence of a wormhole. Maybe not a physical wormhole, maybe a mathematical artifact, but the point is that wormholes are just particular solutions to the classical Einstein equations. String theory is something completely different. String theory came about in the 1960s because people noticed that certain elementary-looking particles that they were discovering at laboratories had masses and spins that were almost like you had a little piece of string spinning around, and that spinning string was quantized, and that quantization gave rise to its masses. So a tiny minority of physicists said, well, okay, let's take little tiny pieces of string and quantize them and see what we get. Maybe we can explain these particles. And they kept predicting the existence of gravity. And they're like, that's no good. We don't want gravity. We want to explain these particles. And then someone taps them on the shoulder and says, gravity exists. You should explain that too. And they realized in the 70s they should think of it as a theory of everything. And they realized in the 80s it is a perfectly well-defined finite working theory of everything. The 40 years later, what we don't know is that it is a theory of our everything. You know, our universe is not everything. Our universe is very specific. 4 dimensions of space-time, certain particles, certain fields. We don't know whether string theory actually gives us the particularity of our world right now. But it is a good theory of quantum gravity, which is a very precious thing in its own right.
Could you tell me more about gravitational waves, please?
I can. That's a good question. You know, gravitational waves are an interesting thing because it provides me an excuse to. I've been talking up this Einstein guy, but he wasn't perfect. He made some mistakes, and the question of gravitational waves is a tricky one because, in general relativity, you know, we talked a lot about coordinates and their relationship to curvature and lengths and things like that, but it's a subtle issue, and in flat space-time, it's kind of obvious what coordinate system to use. In curved space-time, it's not. So for a long time, people wondered whether or not what we thought were waves of gravity, which is easy to write down. Like we knew about electromagnetic waves, just do the same thing for gravity. You could do that, it looked like they existed. But people said, well, maybe they're just waves of coordinates. In other words, they're just bad coordinate choices. There's nothing physical going on at all. One of these people was Albert Einstein. And I think the 1930s, or maybe it was the 40s, he submitted a paper for publication to the Physical Review, and scientific publishing was changing at the time. So the editor of Physical Review sent it to a referee, which was a newfangled thing at the time, getting your paper refereed, peer review. And the referee found a mistake in Einstein's paper. And the editor sends it back to Einstein. Professor Einstein, there's a mistake in your paper. And Einstein wrote back saying, I did not send my paper in to be reviewed. I sent it in to be published. And he never published in that journal again. But the referee was right and Einstein was wrong. And in fact, I don't know whether Einstein ever knew this or not, but we know who the referee is. It was a guy named Robertson who talked to Einstein later, and by the time Einstein got his paper published, he got it right. So the clincher in the minds of many people, as often is the case, was not a technical paper. It was a offhand, coffee break remark by Richard Feynman, who went to a gravity conference and said, look, imagine I have a bar of metal, and I put 2 hoops on it, like 2 rings hanging from the bar. As a purported gravitational wave goes by, it will move the rings. You can calculate that. Therefore, this wave can do work. Therefore, they're real. They're not just a coordinate artifact, and that kind of convinced people. And it was clearly, once you got the math right, it was clearly a prediction that if space-time can curve, it can curve back and forth, those propagate at the speed of light, but gravity is a super-duper weak force. So they're extremely hard to measure, and it's very easy to get messed up by background noise and things like that. So when Kip Thorne and others, Ray Weiss and others proposed what we call LIGO, do we have a picture of LIGO here? No, but we have a picture from LIGO on the left-hand side there. That's the data. This has been under contemplation since the 70s and 80s. And this was a $1 billion experiment, and many, many people thought they would see nothing. I remember as recently as the year 2000, I hosted a visitor from LIGO to give a talk at the physics department, and afterward, the physicists, my fellow faculty members, came up to me and were like, that is never going to work. And it worked. And some physicists aren't always right, but it's a brand new thing. We haven't had detection of gravitational waves for very long. We just a few weeks or months ago found a whole new way to detect them by looking at pulsars and timing them. So we're looking at now very, very long wavelength gravitational waves pushing around pulsars in the universe. This is opening a completely new way to do astrophysics. So whenever that happens, historically, we learn something dramatic and new, and I'm very much looking forward to what we learn from gravitational waves.
Wow, that is a good question to end on, because I'm afraid we've run out of time. But Sean will be outside signing some books. So if you do have some questions, you can try and ask them there. But I just want to say thank you very much for all the brilliant questions from the audience. Thank you for joining us tonight. And please give a huge round of applause for Sean Carroll.